Well, good evening, everybody. My name is Steve Runnels. I'm the Warning Coordination Meteorologist with the National Weather Service in Springfield. And joining us this evening is Corey Rothstein, one of our meteorologists at the National Weather Service. Corey?
Yeah, thanks for the intro, Steve. Like Steve said, I'm a meteorologist here with the Weather Service in Springfield. I've been in the area going on about 3 years now, and I've seen my fair share of events, but wasn't around for this, but I've heard plenty of stories about it. I'm sure a lot of you were there to actually witness the event in person as well.
Absolutely. This was kind of a neat event. Yeah, unfortunately, there were, Corey, 2 fatalities?
That's correct.
So it was a deadly event, but it was an event in which the National Weather Service in Springfield, for the very first time, utilized dual polarization radar. And if you're not familiar with that, Corey's going to include that as part of the training. But ultimately, this dual polarization radar capability does give meteorologists the ability to say, for sure, a tornado has touched down. And as we found with the Joplin tornado back about 10 years ago now, 2011, if we can confirm the threat, people will go quicker to shelter. So by us utilizing dual polarization or spotter reports, it does help us to enhance response and save lives. So if you are brand new to go to webinar, you do have the ability to ask questions or even just provide insights. I think in a second here, Corey might even ask you a question or two about Leap Day. But with that said, I am going to turn things over to Corey. And Corey, if we get any questions pop in, I will come back out and let you know and have you answer them for the audience. So with that said, Corey Rothstein.
All right, thank you, Steve, for the introduction. And actually, since you did just list the way that people can record conversation or even questions, I asked that anybody who was around during the Leap Day tornado, whether they were impacted or directly by it or present during the time, maybe even working during the time that the tornadoes were ongoing, to put some sort of comment into the questions pane as to where you might have been and how it might have impacted you. Anybody in there, Steve?
Yes, in fact, one of the hardest hit communities obviously was Branson, and Ben Bonner says, yes, I became involved at 7 a.m. that morning for the city of Branson. Yeah, Ben, if I'm not mistaken, I think we met up at the fire station about 7:30 or so that morning, so just as daybreak was occurring. I also have Cruz Newberry, who was within about a quarter mile of the Kimberling City, Branson, Kissimmee Mills tornado that night. And that is something to point out. This tornado did occur after dark. This whole event occurred after dark. So consequently, we were probably lucky that we only had those 2 fatalities.
Right, yes, we are very lucky for that too, especially with the high impact areas that were hit as well. Like you said, we had Branson, had 1 fatality, and then also the damage to the Branson Strip itself, and then also up in Dallas County in the Buffalo area too. And so, since a lot of you are familiar with this, that's why we decided we were going to use this case as a way to show how dual polarization radar is useful for tornado detection, how we've been using it for the past, I'd say we're going on about 9 years now. How its usefulness for not only detecting tornadoes, but also giving a heads up to you as the partners and to the public of an ongoing tornado threat. So just want to go over a quick overview here of what this presentation is going to entail. So I'll start off with just going over a brief overview of the actual event itself, what sort of tornado warnings, severe thunderstorm warnings we were putting out that day, how active the event actually was. And then before we dive into the specific tornadoes themselves for the Buffalo and Branson areas, I want to do a little bit of a radar lesson on dual polarization radar, since many of you might not be very familiar with it. And it also will help set the stage for what we're actually looking at on the radar images later on in this presentation. And then finally, we actually will use the leap day tornado event, again, focusing on the Branson and Buffalo tornadoes for actually detecting tornadoes on radar. So as you can see here from this image, we have what were all of our severe thunderstorm warnings for the entire event in yellow, and then our tornado warnings in red. And you'll notice that there's a lot of these little, we got wind reports, tornado reports, hail reports for the entire event. And actually what happened is we had a squall line of storms that moved across much of the area during the overnight hours on February 28th into 29th. Ended up producing about 8 tornadoes during the early morning hours, and luckily most people were not injured or hurt, and we only had a few fatalities with that event. Again, some of these tornadoes are actually somewhat strong for what we usually see with squall lines. 3 of them actually were EF2 tornadoes, which is not in the high end in intensity, but certainly a strong tornado with respect to a lot of what we see around here. And then we also had 5 EF1 tornadoes. And again, like I said, we had 2 fatalities, an additional 53 injuries with the tornadoes throughout the course of the night. And then, like I said before, also 50 other non-tornado reports in the forms of hail and wind damage from not only the tornadoes themselves, but the squall line and some embedded supercells that went through as well. So what I have highlighted on the map here are the rough paths of the 8 different tornadoes that occurred during the overnight hours on the 28th into the 29th. Again, you'll see that the 2 paths and the ones that we'll focus on later are the Branson tornado, started over Table Rock Lake near the Kimberling city area, and then moved eastward into portions of Taney County. And then the Buffalo tornado, which was not on the ground as long, but still, again, caused damage and injuries. So what was the big case of this event? Why is it the specific event that we're focusing on? Well, the funny thing is, about 2 weeks prior to the event itself, we had actually upgraded the radar to allow for dual polarization. And we'll touch on this a little bit later as to what the main difference is that compared to just regular radar data. But prior to that, main uses for or what we were looking at and assessing storm intensities with was just reflectivity data and then velocity data on radars. So this event served as a catalyst for being able to actually see tornadic debris signatures, or what I'll refer to after this as a TDS on the radar, and we actually saw 4 of these different TDSs throughout the course of the night. Another big reason why we're focusing on this event is because not only did it cause high impacts to the Branson Entertainment District, but it also got a lot of local and national news coverage due to the high impact event, as well as the injuries and fatalities. So before we go into the actual radar data on the event itself, I want to touch on some of the different radar features, as well as the dual pol information on radar and how we can use it to assess tornado detection, as well as potentially if the tornado is still ongoing. So what we have here is your typical WSR 80AD radar. You'll see this if you go to the Springfield Branson Airport, make a drive up toward the northwest side of Springfield at all. So that just sits there and it's turning around 24/7. What we have on the right here is just your stereotypical, let's call this just a general thunderstorm. And what happens is the radar will send out multiple pulses per second, on the order of hundreds to even around 1,000 pulses per second, out towards this storm itself. And now there's smaller, say, hail, you have rain, there's different particles inside that storm that the pulses will actually bounce off of. And then some of those pulses will actually be returned to the radar here. And then it'll actually output what you typically see as the just normal reflectivity data that you'll see on the radar screen, whether on TV or on an app on your smartphones. So how is that different now that we have the dual polarization in the mix as well? Well, normally, prior to the dual pol being implemented, we only had pulses going in one direction. So you were really only getting a cross section of any of these particles that you were hitting in the storm, whether it be snow, hail, or rain, and having that sent back to the radar. But the big difference now is that we had pulses going in 2 different directions, so we can get 2 different cross sections of the particles that we were hitting. And what does this do for us? Well, it gives us a better understanding of what we're actually seeing in the storm and allows us to assess what kind of particles specifically we're seeing and not just the size or the intensity. So in addition to that, not only is the radar sending out pulses in the horizontal and vertical in just a straight line, we also have multiple different elevation that the radar is also scanning through a storm as well. So these the storm will go around in a circle. It'll shoot out the pulses and measure at different elevations as we go up. And then as those different cuts through the storm will give us a different cross section of the storm at different heights above ground level. And using enough of these slices, we're able to actually get an entire scope of the storm and what it actually looks like to us from as upwards of 80, 100, even further up to like 120 or more miles away. So let's take a look at some of the radar products here. Give it just to set up the stage for dual polarization and helping you guys understand better what it actually is. So again, like I talked about before, we have our generic standard reflectivity or Z images that you'll see on radar screens across TV and your apps a lot. So again, this is the power of that pulse that was sent out from the radar returning to the radar, and then that shows up on the screen in different color coding. And depending on what you're looking at in terms of your radar app or on screen, the colors might vary a bit, but the main story here, the main gist of it is as you're getting into these warmer colors, you're tending to see larger raindrops, higher rainfall rates, and then as you get into even like higher colors, potentially even seeing some hail in there as well. And again, this will help us determine how heavy the precipitation is and give us just a slight indication of what type of precipitation we're actually seeing. Now, there's two different types of velocity. The one I'm going to focus on here is a little bit more useful when trying to detect tornadoes. You do have your standard velocity, but what we have here is the storm relative motion. And the main difference between the two is the storm relative motion is going to be your radar velocity, but we also subtract out the motion of the storm. So for example, if you have a storm that's moving east at 30 miles an hour, we're subtracting out that eastward movement out of the storm so we can highlight the features of the storm better, specifically with supercells looking at the rotating updraft in the storm. And just to give you an idea of what this image is actually showing, here's the radar down here. You got Willard just north of there, this little donut hole of a circle. Any green values are actually storm particles such as rain or hail, or even some biological like bugs and birds and stuff. If it's green, it's actually moving towards the radar, and then red is actually moving away from the radar. So I have any questions there with the standard radar products before I get into the dual pol products?
Corey, we haven't had any questions come in, and I'll give you a chance to type in your questions for Corey. I do want to mention we had a few people provide some additional detail of what they were doing that day. Cruz Newberry mentioned that there was a fishing tournament going on in Table Rock Lake, and one of the inns that several people were staying at, the Kimberling Inn, was impacted directly. So while we talk a lot about the Branson aspect of this event, we do recall also that the fishermen were affected there at Kimberling.
Right.
And Ben Bonner also mentioned that if it had been a week later, there had been a NAIA tournament at College of the Ozarks. So we kind of got lucky there as well.
Right.
Again, if you have questions for Corey, please put them in your the question box. And it's not even just questions. If you have insights or comments in general, please share them with us. Corey?
All right. Thanks, Steve. All right. So without any questions, I'll get into describing some of the different dual polarization products that are available to us, as well as to you on many of your apps as well. So the first one to help with detection of tornadoes is called what we call differential reflectivity, or ZDR. It sounds kind of technical, but essentially what it's doing is comparing the power from the pulse that's reflected off of the particles in the storm. And it's comparing your horizontal and the vertical pulses and how those compare to each other we can use that output to determine what type of rain or hail even that we're actually seeing in the storm. And so for more of your particles, like your smaller rain, that tends to be something that's a little bit more of a sphere. So it's uniform in both the horizontal and vertical directions. That tends to give you a value for ZDR of about 0. Now, as we get into the larger raindrops, what you tend to get is a little bit of drag as the raindrop is falling through the air. And what that tends to do is cause it to go from more of a spherical format to more of like a hamburger bun is usually what we tend to call it, or at least I call it that, in appearance, just because it's getting squashed a little bit in the vertical direction and being widened a little bit in the horizontal direction. So when you have these types of what we'll call them hydrometeors, that encompasses rain and hail, those will tend to give you a ZDR that's actually positive. And another comparison you can also look at is some particles that are actually taller in the vertical than they are in the horizontal. And what that tends to do is give you a negative ZDR. And this is stuff that'll be important a little bit later on, and also explain it to you on the next slide here. This tends to be more what's associated with hail, because the hail, especially as it gets larger, tends to be favored in one direction or the other and is not necessarily spherical. So this graph here essentially shows your values ranging from the negative ZDRs up to the positive CDRs, and then the different types of particles or hydrometeors that you would see and the values associated with those. So again, like I said, your rain that's smaller tends to be more spherical, so you're seeing values that are closer to 0. But as you get to a larger drop size, getting into those really large drops that tend to splat when they hit the ground, you're starting to get into really higher values. Again, with the hail, your smaller hail tends to be a little bit more spherical, and then as it gets bigger, it actually gets to a certain point where if it's big enough, it'll be a negative ZDR value. But between that time, there also might be some rain mixing in with the hail that could cause values to actually be a little bit higher. Now, the main thing to focus on for tornado detection is actually going to be your debris. And your debris doesn't usually have a preferred direction because it tends to be tumbling as it's falling or rising through the air. And so because of that reason, most of your values of debris for ZDR are usually going to be around 0, or they're going to actually be even slightly negative. Our next dual polarization radar product is a correlation coefficient, or CC as I'll refer to it from now on. Mainly, this is a measure of how similar your horizontal and your vertical pulses are from scan to scan, as opposed to on a single scan like ZDR is. And so if the orientation of your hydrometeors are changing from scan to scan, you're going to see values that are less than 1. So if it stays uniform from scan to scan, you're going to have values closer to 1. And a lot of that's going to be like your smaller raindrops, even as you get into larger raindrops, as long as they stay consistent in size and shape, or even some snow. Those values are tending to be very close to 1. Now, as you get into your hail, especially as it gets larger and it starts to tumble or even stack vertically, you're tending to see your CC values getting closer to about 0.8 to 0.97. And then when I talked about before, like when we're seeing with our birds or our insects or even bats or even debris, what you're really seeing is these really don't have any consistency from scan to scan, because they're not consistent. They're not, that's the easiest way I could really put it, is it changes from so much from scan to scan that you tend to have very low CC values. And again, when it comes to focusing on tornado detection with CC values, again, it's that 0.8 value or less with debris that you tend to see associated with the lower CC values. So let's put this into context a little bit. I know it's a lot of stuff I've been throwing at you. I just want to show you how it actually happens, or how we use it in real life. And a recent event that just happened was the long track tornadoes in Alabama. And what you can see here on the image is the CC drop, or the values that are lower than 0.8. So the values that are typically these greens into these blues, or even the dark blues. Because that's in a tight circle here, you have pretty high confidence that this is actually an ongoing tornado. And each of these scans is actually at a different height. As you go up in height, you can see that this is pretty uniformly dispersed between the two, so it's stacked pretty vertically with height. So that gives us additional confidence into this actually being an ongoing tornado, which it was. And the tornado was actually on the ground for 80 miles, caused a lot of damage to numerous trees over that course of the hour and a half plus that it was on the ground. Even some damage to houses and cars as well. And again, just wanted to point out, just because not only is the CC values low here, but it's more of a larger concentration of those low CC values that will help give you confidence in indicating that it's actually debris that it's scanning in the air. Do I have any questions on that before I go into some of the tornado signatures on radar?
Not at this time yet, Corey. And I think you hit it very well with that Dixie Alley event. You know, the signature was extremely clear with that particular tornado, but sometimes these CC signatures don't quite correlate with reflectivity or the circulation. And it could be something that you think is a tornado, but it has to be correlated with those other two features before it actually is. Unfortunately for the folks down in the southeast, that particular event, it was pretty clear.
Right. And yet, like I said, I'll be digging into that pretty soon here too, but I like that you highlighted that there's going to be 3 different things you need to focus on in order to have confidence in it being a tornado debris signature. And there's actually even a fourth thing that you need to know to give you even a little bit more confidence that it's a tornado.
Hey, Corey, before you go further, we did get a question come in. Does it take a very large quantity or amount of debris to reflect and show on radar?
Not really, actually. I mean, it's hard to quantify, but you don't really need that much debris to actually have it show up on radar. And a lot of times, especially with some of these weaker tornadoes during like the fall or even the winter seasons, you have a lot of leaf litter on the ground or even small twigs that these tornadoes are picking up and throwing into the air. So those can actually make it easier to see the tornado. So you don't necessarily need something that's big or a lot of debris in order to actually see these. All right, so let's take a look at some of the different radar features that help us get confidence in that we're actually seeing a tornado or something very close to when a tornado is going to occur. So the first one here is what's called the tornado vortex signature. And again, as I talked about before, your green values on the storm relative motion are actually going to be moving towards the radar, which is actually over here to the right side of the screen. And then your red values are going to be what's moving away from the radar relative to the radar. And because of this, you see that you can imply with these winds going towards and away from the radar that there's implied rotation here. And as you get into these higher values too, right next to each other are what we call gates or an individual scan on the radar image itself. That can also indicate what we call a tornado vortex signature. The problem with these though is they're not often showing up on radar, especially as you get 40, 50, even 60 miles away from the radar, just because as you get further away from the radar, you're scanning higher up into the storm, so you might actually miss some of these lower level features that usually don't occur that high. So it's something to keep in mind that oftentimes you're not even going to see this signature. And going back to what Steve had talked about before, so there are 3 different requirements for a tornado debris signature or a TDS. Just want to show quick in the image to the right, we have our Z, which is our reflectivity, our SRM, which is our storm relative motion, our CC, which is in the bottom right, which is your correlation coefficient. And then as we talked about before, the ZDR in the bottom left, which is your differential reflectivity. And so the first requirement for picking out a tornado debris signature is that you want to have that couplet of inbounds and outbounds very close to each other. What we say as an azimuthal couplet, it means that in this case, your radar is up actually to the top part of the screen. You want these greens and these reds to be perpendicular to each other, or the line between the two perpendicular to the radar beam itself to imply rotation. Otherwise, if you have, say, your green, let's look for over here, for example. Say you have your red here, which is showing that the winds are actually moving away from the radar, and your green here, which shows winds moving towards the radar. You actually have what we call a convergent pattern, which doesn't imply rotation at all, and that's just convergence of the winds. They're coming together in that location as opposed to rotating. So what do you want with that? Well, you want that to also be located in the same spot or very near the same spot as a very low correlation coefficient value, typically, like I said, of 0.8 or less, to give you high confidence that you have debris ongoing in the air that the radar is detecting. And with that and the couplet, and then also the last feature, your reflectivity values of greater than 30 on here, which again, depending on what you're using for an app or on TV, your colors might be a little bit different, but typically you're getting into your warmer colors with your 30 dBz or higher. So if those are all co-located together, you have fairly good or even high confidence that there is a tornado ongoing and debris is being lofted into the air where the radar can scan it. And now I talked about this fourth confidence builder on here as well, and that is with your ZDR. You'll notice in this image specifically, your ZDR is either around 0 or even slightly negative. And what that does, like I talked about before, is you have debris that's not preferred in any one direction. It keeps tumbling as it's going through the air, which is giving you a ZDR near 0. So that again gives you more confidence that there's a tornado ongoing at this time. All right, Steve, did I have any other questions from that before we actually get into the radar images for the event?
The only question that came up was the location of the radar. And, that's a very astute question. And I know you had said it's up to the above or to the north in this particular case, but
right.
But can you go back over how critical that is as far as knowing where the radar is in reference to the rotational data?
Sure. Yeah. So again, like I said before, assume your radar is towards the top of the screen here. You want your what we call a couplet of the outbound velocities in red and your incoming winds in green towards the radar. If that's perpendicular, so you'll see the axis between the two is kind of from the bottom left of the screen towards the top right of the screen. Since your radar is up here, it actually kind of creates what we would have like a T to show that it's perpendicular to the radar beam. And because of that, you have implied rotation. And again, then to show which is more of a convergent signature rather than a rotational signature. If you go down here a little bit to the southwest of that location, you have green, which is showing the winds coming towards the radar, and red with winds going away from the radar. And since those are coming to each other, the winds are actually coming to each other at that point as opposed to rotating around. It just builds more confidence when you are perpendicular to the radar. So keep an eye on that because there are some instances where that could trip people up. All right. So let's get into the leap date tornadoes, and I know that's why you're all here. So less with the technical stuff and more into actually looking at the graphics. So let's talk about what the event setup looked like a few days beforehand. We talked about before the Storm Prediction Center actually had highlighted this event several days in advance as a potential for some severe weather that day. In this case, having a slight risk for severe storms over portions of the Arlitex region, even up into the Missouri Ozarks. By day 2 or the day beforehand, you still had that risk showing up again over southern portions of Missouri, over our portion of the area, and also portions of eastern Oklahoma and northern Arkansas, or actually much of Arkansas. And then by the day of, so 7 a.m. prior to that event, so about 15 hours beforehand, you're already seeing that risk has expanded for severe weather to include much of the area across southeast Kansas, southwest Missouri, and even south central Missouri as well. So what are some other products that we use in order to assess the potential for severe weather and tornadoes? One of them here is what's called a mesoscale forecast discussion, or an MCD, and that's just a product that the Storm Prediction Center will issue closer to an event when they're expecting that there's going to be some ongoing wind or tornado threats that are going to be imminent within a few hours. And again, this situation for that day, we had a cold front that was draped across eastern Kansas, and then the highlighted threat area was going to be as we were getting into the earlier portions of the squall line that developed. So the threat right now at this situation was actually highlighting western Missouri and southeast Kansas. And as we got a little bit later, shortly after that, actually, we got to about 10:30 p.m. You'll notice that there was a tornado watch issued for most of northwestern Arkansas, and then our entire warning area in southeast Kansas and southwest Missouri, as well as portions of south central and central Missouri. So a little bit shortly after that watch was issued, there was a new mesoscale discussion that was put out, highlighting the threat for primarily damaging winds and tornadoes with the Boeing segment of storms, or the squall line that was moving across the area from west to east across southwestern Missouri. And that's, again, if we refer back to what I talked about at the beginning, that's where you started seeing all of your tornadoes developing in the line up here over in the Dallas County, Laclede County area, and then also getting into the Table Rock Lake and even into the Branson area as well. So like I said before, we had mainly a squall line was our primary storm mode with this event, but there was also a little bit of some embedded supercells. So a supercell thunderstorm structure kind of inside the line itself. And because of that scenario, we had some fast moving storms as well as an atmosphere that was primed for some very rapid tornado development. And having dual polarization radar actually was a lifesaver for this event, because these tornadoes would develop very quickly. We could actually be able to see some of those on radar as they developed. So the first storm was the southern storm that we'll refer to, and this actually occurred about an hour after the Dallas County storm, but we just wanted to highlight this one first. So this was the storm that produced a tornado that started near Kimberling City and moved through Branson and into Powersite before lifting. That tornado, again, was another strong tornado, EF2 with path length of about 22 miles. The storm with this we're actually more confident that it was a supercell, and the main reason was because there was circulation in the radar velocity at multiple levels throughout the duration of the storm as it moved in from Arkansas. So that's why we were a little bit higher confident, because of the rotating updraft, that this was a supercell. As the storm got into Table Rock Lake, it actually had the circulation tighten a little bit. And then the initial development of the tornado, again, like I said, near Kimberling City. And you can see that radar couplet again. Again, the radar is up to the top of the screen. So it's, again, you draw that T here through the couplet of the inbound and outbound velocities. And you'll notice that because this is perpendicular to the radar, you do have rotation here in the Branson area on this image. So at 1:09, at this point in time, the tornado was on the ground, and you'll notice that there's nothing that really shows up at the moment on our, let me back up a little bit here and explain what these images are. So the top left, again, is going to be your storm relative velocities, or your storm relative motion. The top right is going to be your ZDR, or your differential reflectivity. The bottom right is going to be your correlation coefficient, and then your bottom left is going to be your reflectivity data. And again, so at this time, we do have that couplet on the northern side of Table Rock Lake near Kimberling City. But you notice that even though the tornado is on the ground at this moment, and the reason that we were able to figure that out is after the fact, we did a survey and found that this was actually when the tornado started. So during the event itself, you would not have been able to pick up that the tornado had started already on radar. But what tends to happen with the debris is it takes time to get lofted into the air. So you're not going to see it right away when the tornado might already be on the ground. So you go 5 minutes forward to 1:14 a.m. and the storm is now east of Kimberling City with the tornado. And you'll notice now that we have all three of the features that we need to be confident that this is actually a tornado ongoing on the ground. And you'll notice, so you have the couplet here east of Kimberling City. We also have the drop in ZDR, that gives us some confidence there, as well as a drop in the CC values, which in this case are around 0.8. Usually you'd like to see them a little bit lower, but again, that's with this tornado just starting to loft the debris into the radar. This is giving us some more confidence. And then that's also collocated with some higher reflectivity values as well. As we go forward another 4 minutes, you again see that there's a tight circulation that has now just crossed over into just west of Branson on the east side of Table Rock Lake. Again, you still see that the ZDR is low, and you have your CC still ongoing as well. So there is still tornado on the ground at this time as it's getting close to Branson. Stepping forward another 5 minutes, this is when the tornado actually makes an impact in Branson itself. It impacts the Strip as well as the Branson Hyatt Hotel. And again, because those signatures are all still present, we are still confident that the tornado is on the ground. And it actually continued for several minutes after that, got into the Powersite area where you still had the low CCs, the low ZDR, and the couplet still present on radar. And then by about 1:37, you'll see that the storm is actually weakened. The tornado or the radar velocity couplet is no longer there. There's no reduced ZDR in that location anymore as well. And then the correlation coefficient is no longer as low there either. And don't be distracted by this. While you have low CCs here, you also notice that this is a location that has higher ZDRs and also isn't located with a couplet at all. That most likely is just going to be an area where you might have some hail in the downdraft of the storm. So again, this photo is from Springfield News Leader. Again, it shows the substantial damage that was seen to the power poles along some of the roadways in Branson. And then we also have the damage to not only a bunch of windows on the Branson Hyatt, but also to the canopy there as well. So before we get into the northern storm in Dallas County, do we have any questions for this one?
We do not have any questions. Ben did remind that it's the Hilton rather than the Hyatt. But yeah, it just strikes me that at 1:09, in February, so 1:09 a.m. in February, can you imagine 1:09 p.m. in say May or June along the Strip in Branson? So in many ways, tornadoes after dark lead to even greater fatalities, but in this case, we may have been a little lucky.
Right, especially since we weren't in as much of a tourist season by that point too. So luckily, I mean, it was still horrible that there was 2 people that died and 53 injuries, but like you said, it might have been substantially higher had this been during the day, during more of the peak of the tourist season.
We did get a question in from John McBride. Were there any reports from the ground from Kimberling City? Do you happen to know the answer to that, Corey?
Not off the top of my head, but I can go back to the, I did have the image prior to this that had the reports, or not prior, it was earlier in the presentation. I can get back to that at the end here once we're finished. But at the moment, off the top of my head, I'm not positive on that.
If memory serves correctly, emergency management director over in that area, Tom Martin, did report spotter reports. So we kind of knew something had happened at Kimberling City. We probably didn't quite know that it was tornadic, but the next reports we started getting in from Branson itself, there was no doubt at that point in time. In fact, even maybe some indications a strong, if not violent, tornado with reports of concrete blocks flying across 65. So yes, spotters in the Kimberling City area did provide some degree of indication that an event had occurred, but we did not know it was tornadic until it really struck Branson. We also have another question came in. Does the more rugged terrain found in this area present any unique challenges?
It can, yes. Specifically when it comes to surveys, especially if you get into the more rural, rugged areas, sometimes it's hard to find damage when there's roads few and far between. to access the damage. As far as impacts to the radar itself, I'm not aware of any significant beam or blockage of the radar beam due to the elevation changes. So I haven't seen many issues from that, but it tends to be more of an issue when we're going out and doing surveys on tornadoes. And Steve, I'm glad you brought that up regarding the Tom Martin and the spotter reports. We love that the spotters give us reports all the time, and it's oftentimes a good way for us to get reaffirmation of what we're seeing on radar on the ground. And unfortunately, with events like this and ones that specifically occur at night, is those spotter reports become few and far between, mostly because people are sleeping, but also because we don't recommend that people go out and try to spot tornadoes, even severe weather at night, just because of the impact to their safety. And so using the dual polarization on the radar and this tornado detection, we're actually able to detect the tornado in more real time than maybe a report that would have come in upwards of 15 or even maybe 30 minutes later, once we actually realized what was going on there. All right, so let's step back an hour from what happened in Branson and move up to the Buffalo area. Here was another tornado that we did have a fatality from, unfortunately. Again, it was another strong tornado of EF2 in strength, and it only wasn't quite on the ground as long, but it had still a path of about 10 miles, and actually lifted for a little while there before there was an additional tornado that touched down as we got into the Lebanon area. That one was an EF1. So again, the focus here is going to be on the two different circulations between those two tornadoes. So at this point in time, 11:56 p.m., it's dark out, not getting any reports of anything. You don't really see much on radar. There isn't anything in terms of, any rotation, significant rotation on the radar data and the velocity. I'm not really seeing any features in terms of anything that would point to a tornado either imminent or on the ground at the moment. By 12:05, you'll notice that there is a substantially stronger circulation that has now shown up just southwest of Buffalo. Again, you have your radar is actually off to the southwest here. So you're actually seeing your reds being your winds are actually moving towards the northeast on this side of the storm, and then on this side of the circulation, it's actually moving towards the southwest. So we do have the rotation here again. And then if you look closely, it might be hard to see, but we do have the reduced ZDR here as well. That's round or below zero with the blue and the gray values. So that's giving confidence when you also see it co-located with low CC. And then actually what we would call here a debris ball on radar. What that tends to be is just an elevated values of reflectivity co-located with that TDS couplet. And when we say elevated, they tend to be pretty high in values, like you get into the 40, 50, even maybe 60 dBz or value range for reflectivity. So at this point in time, we're very confident that there is a tornado ongoing just southwest of Buffalo. And some of the damage here that's actually showing up and causing this TDS on radar was damage to an outbuilding in that area as well. So we step forward about 9 minutes. The circulation is not quite as intense as it was before. It's actually loosened up a little bit, but you do see that there is still some lower ZDR as well as low CC co-located with that couplet. Again, it's starting to spread out at this point now. And usually when you're seeing the TDS, the values, or the lower CC values, tend to be more in like a circle and be somewhat tight and close to each other. As you get a little bit later, and maybe even a storm or a tornado has briefly lifted, you can get the CC values to actually start spread out on the radar. And the reason being is that your debris is also being, as it's lofted into the storm, it's spreading out. And that's what we're actually seeing here. We go forward another 5 minutes, the circulation begins to start intensifying as it gets into Laclede County again. Again, you do have just southeast of Long Lane, you do have that lower ZDR, as well as the very low correlation coefficient values, again, co-located with some higher reflectivity. Again, that's giving us confidence that the second tornado and TDS is actually on the ground, so it's ongoing at this moment. Step forward to 12:23 a.m. Again, the circulation is still very tight. We do have the lower ZDR here, and actually a CC as well. And then we're still confident that there's ongoing circulation, tornado ongoing at this time as well. You notice there. Sorry. And then by the time we get to 12:33, about 10 minutes later, again, the circulation's weakened a bit. There's not really any indication that there's much in terms of an ongoing tornado threat anymore. And by this point in time, the tornado had lifted. Okay, so let's take a look at some different elevation scans of the radar. So as you go up in degrees, so like you have a half degree here, 1.5, 3.4, 5.3. As you're going up in degrees, you're actually going higher and higher in a radar scan in terms of elevation above the ground. In terms of from the distance from the radar here, this is several thousand feet above the ground as you get into like this 5-degree scan. So again, at 12 a.m. before the tornado, you don't see anything on radar in the correlation coefficient data, which is what we're looking at. Then by 12:05, you get that circulation showing up at multiple levels in here with a lower CC. So your TDS is ongoing, or your tornado is ongoing at the moment with the TDS. And this is something else I wanted to highlight as well. Oftentimes people will get locked into the lowest radar scan. That's all fine and dandy, but when you're trying to assess not only tornado intensity, but whether or not tornado is ongoing or developing, it's good to be looking above that lowest radar scan to get more information as to what's actually going on in the storm. So step forward another 5 minutes, again, that the low CC values and TDS is still present, and it's actually even gotten up to about 5 degrees now. And as we move forward with the storm, this continues to go on for several more scans, which is on the order of 10, 20 minutes before the debris starts to just spread out and the tornado is actually ending at this point. All right, so do I have any questions with that second storm? Otherwise, I'll move into how we utilize this with communicating to you, the partners.
You're good to go.
Okay, all right, we'll go right into that. So with this event, another thing we wanted to highlight is how we use the dual pole radar features to actually give you, the partners, heads up during this event, especially since there wasn't much in terms of spotter availability and it being at night. So we did make some calls to the emergency managers in the counties that were affected, which has resulted in additional warning actions, specifically downstream warnings and talking with them, getting the damage information from them, also giving them the information as to what we were seeing on radar. We also utilized NWS chat to give the media added confidence for mentioning confirmed tornadoes on air to the public. And again, with that confirmation of a tornado on the ground, you tend to get more of a appropriate action from the public in terms of seeking protection for themselves and going to their safe place. And actually with the Lebanon tornado, and I had referred to this before, occurred about 10 to 15 minutes after the Buffalo tornado. With how fast these storms are moving, it was difficult. And at night, it was difficult. If we did get reports, they could have often been too late for us to actually get a warning out for those tornadoes by the time they started. So again, just want to highlight this from our warnings. What we highlighted here is there's strong indications from spotters and from the radar that a tornado is on the ground using those different features that we looked at here, moving through the city of Branson. And it's hard to read down here, but this is just a snippet from the NWS chat that we had that night. Mike Griffin, one of the meteorologists here formerly now in Cleveland, the Cleveland office, was saying Doppler radar and dual pole is showing strong indication of a tornado now on the ground near Kimberling City and going into Indian Point, just south of Silver Dollar City. And then we had several reports of funnel clouds, rotation, even Kevin Leidy saying thanks for us, doing great. And then as we got into the Branson area, especially just west of Branson, Seeing that strong circulation co-located with the debris that we were confident the radar was scanning into and confirmation of a tornado, we were able to say that there was a strong indication of a tornado on radar, with the latest scan showing the tornado just west of Branson. And that wraps up pretty much what I wanted to talk about. We'll open it up for questions here in case there's anything that you guys wanted to ask me.
Let's see, we had a couple questions on lead time on going back to the Branson cell. Had several comments on your presentation skills, so they're enjoying your presentation, Corey.
Appreciate that. Thank you.
Multiple people are saying that. I'll give one observation. You know, sometimes it is difficult for us to determine whether or not these a particular damage path is tornadic versus wind. And of course, the Branson event that was extremely clear. But one of the memories I have from the Buffalo event is, unfortunately, a home had been hit, so insulation was flying through the air, and it was actually a rain wrap tornado, so that insulation stuck on all sides of structures. So again, it was pretty clear pretty quickly that a tornado had moved through that particular jurisdiction. Teresa Coldiron asked, can you email a copy of this presentation? We would be glad to do so. Also, Teresa, we are recording this, so you'll have the opportunity to share that link as well.
And Steve, if I'm correct, we will be posting this on our YouTube page as well.
Absolutely, yes. All the presentations that we have done going back to the start of COVID, and actually even beyond that, but going back to May and June of last year, are available on our YouTube. And before we close here, I will dig up that link as well.
I've got the link right here too.
Oh, yes, if you got it, please feel free to print it.
So again, yeah, our YouTube page will be youtube.com//NWS Springfield. And then like Steve said, he'll be sending out the email as well with the recording once we get that finished up here. Any other questions or comments?